Hello everybody, welcome to another lesson by me, Miss Pythagoras. In this lesson, I will explain Euclidean geometry, more specifically the proof of the theorem of Pythagoras as well as an example. This is lesson 5 of 11. The theorem of Pythagoras states that in a right-angled triangle, the square of the hypotenuse side is equal to the sum of the squares of the other two sides. And then the abbreviation by now you know is Pythag. So required to prove is that BC squared is equal to AB squared plus AC squared. And we'll do the proof now on the next slide. Let's start with the proof. Given is triangle ABC, that's the big triangle, with angle A 90 degrees. Required to prove is the theorem of Pythagoras, which is BC squared is equal to AB squared plus AC squared. And with all proofs there's a construction. And the construction, draw AD perpendicular to BC. Now we can start with the proof. So in fact, if you have a look at the sketch, there's three triangles. There's the green triangle ABD, there's the blue triangle ADC, and then there's the big triangle ABC. Now we will work with the left-hand side, the ABD triangle. Now have a look. In triangle ABD, that's the green triangle, and triangle ABC, that's the big triangle, we can say the following. Angle D1 is equal to angle A, and they are both 90 degrees. We can also say that this little angle there, B, is equal to B because it's the common angle. And then without thinking, we can say the third angle, the one that's left now, is that angle A1 in the green triangle is equal to angle C in the big triangle. And your reason, third angle of a triangle. So now we can say that triangle DBA is similar to triangle ABC. And please note the order in which you write that. DBA, can you see DBA similar to triangle ABC, the correct order, and then your reason, angle, angle, angle. Now because of the similarity, we can write down the ratios. DB over AB is equal to BA over BC is equal to DA over AC, and that's because the two triangles are similar. Then on the green triangle, we're looking for the side AB squared. So therefore, this little part there we will ignore. And then just keep in mind, AB is the same as BA. And then we can cross multiply and we end with AB times AB is equal to DB times BC. And remember, AB times AB is AB squared is equal to DB times BC. So that's half of the proof. Now we move over to the right-hand side triangle, the blue one. And we're going to prove triangle ADC, the blue one, and triangle ABC, the big one. We're going to prove them similar. So we can start by saying that D2, angle D2, is equal to angle A. And your reason, they are both 90 degrees. Angle C, which is this one, is equal to angle C. It's the common angle. Without thinking, the third angle, angle A2 in the blue triangle is equal to angle B in the big triangle. And your reason, third angle of a triangle. Therefore, the two triangles are similar. Triangle DCA is similar to triangle ACB. And can you see the order? DCA, DCA, similar to triangle ACB. And your reason, angle, angle, angle. Then you write down the ratios. DC over AC is equal to CA over CB is equal to DA over AB. And again, we will wait with one of them. Let me just decide this one. Keep in mind, AC and CA, it's exactly the same thing. Therefore, we can cross multiply and we end with AC times AC is equal to DC times CB. AC times AC on this one is the same as AC squared is equal to DC times CB. Then in the next step, what we will do is we will take the left hand side there was AB squared and the left hand side there was AC squared, and we're going to add them. So we say AB squared plus AC squared is equal to, and now the right hand sides, the ones that's left, is DB times BC plus DC, which is this DC times CB. Then we're halfway there. Now we can pull out BC. BC and CB is the same thing. We can pull that out as a common factor. And we're left with DB plus DC. Now have a look at the sketch. DB is this part over there, which is this part, plus DC, which is that part. And can you see the whole thing is in fact BC. And then BC times BC is BC squared, and there's your theorem of Pythagoras. Now we can say that when a perpendicular PS is drawn from the right angled vertex P of triangle PQR, we get the following. Triangle PQS, that's the green triangle on the left hand side, is similar to triangle PQR, the big triangle, and therefore we can say that QP squared is equal to QS times QR. We can also say that the blue triangle on the right, PRS, is similar to the big triangle QRP, and then we can say PR squared is equal to RS times RQ. And we can also say that the green triangle PQS is similar to the blue triangle RPS, and we can say PS squared is equal to QS times RS. Let's do an example. In the figure, AE is a diameter of circle ANE. L is a point on AN, and LE bisects angle AEN. Let E1 be equal to E2 be equal to X. And why are they equal? Because LE bisected angle AEN. Furthermore, NE produced meets a line from A parallel to LE in D. Hence, LE is parallel to AD. Now the question says, give reasons for the following statements. The first statement states that E1, angle E1, is equal to angle D. Why can we say that? They are corresponding angles since LE is parallel to AD. The next statement is that E2 is equal to A2. The reason? Alternate angles equal, because LE is parallel to AD. And then the last statement, AE is equal to ED. And why can we say that? They are sides opposite equal angles. Before we continue, have you subscribed yet? And a reminder, you can also visit my website, onlinemaths.co.za. The link is in the description below. Also feel free to leave a comment or like my video. Let's continue. Now the next question says, if NE's length is 12 units and the diameter of the circle is 20 units, calculate the length of AN. Now do you agree that angle N is equal to 90 degrees, angle in semicircle? Therefore, we can use the theorem of Pythagoras and say AE squared is equal to NE squared plus AN squared, Pythagoras. And then we can substitute. In AE's place 20 squared equals, and in NE's place 12 squared plus AN squared. 20 squared is 400 equals 12 squared is 144 plus AN squared. Let the 144 walk across and you end with 256. Then you don't want AN squared, you only want AN, therefore you take the square root, therefore AN's length is 16 units. The third question wants us to calculate the length of AL. Remember from the previous slide, AN's length was 16. Now we can say AE is equal to ED, that's given. And remember, ED is 20 units since it was given that AE, the diameter, was 20. Now we can say that ND, the whole of ND, consists of NE plus ED, which is 12 plus 20, and then it makes ND 32 units. Then LE is parallel to AD, that's given. Therefore, we can say AL over AN is equal to the ratio ED over ND. And why can we say that? Theorem 1, the line parallel to one side of a triangle. And now we substitute. We know AN is 16, ED is 20, and ND is 32. So we will multiply away the 16 and we end with AL is equal to 10 units. In the next lesson, I will discuss examination questions from previous metric exams which you can use as part of your exam preparation. Click on the video in the left-hand corner to take you straight to the next lesson.